All right, let's do our next one. Next one is on related rates through triangles. So our first example is an airplane is flying overhead at a constant elevation of 3,000 feet. Ethan is viewing the plane from a spot 4,000 feet from the base of a radio tower. The airplane flies horizontally away from Ethan. If the plane flies at a rate of 600 feet per second, at what rate is the distance between Ethan and the plane increasing when the plane passes over the radio tower? So I started off by drawing a picture. It's not the best plane, but hey, maybe we'll put some wings on it. So the plane's flying over, it's flying to the right. My radio tower is here in blue. That's my radio tower. I don't know how to draw a radio tower. I put a little satellite dish up there. And it says Ethan is viewing the plane a spot from 4,000 feet from the base. So that's what I put there. And it says that the airplane is at an elevation of 3,000 feet. Why do I have 4,000 written right there? That's 3,000 feet up. And so as it's flying over, it says the plane flies horizontally, which means, oops, that's not what I wanted to do. I want to do the highlighter. As it flies horizontally, it means the elevation isn't changing. So it should still be 3,000 feet when it gets above the radio tower. So I made a little triangle here. I did the 4,000 along the bottom here. I did 3,000 along the top. And I called the diagonal distance y. I originally called it d, but when I was taking the derivative, the d's were fucking me up. So I recommend not using d for distance. I made another triangle. This is the same triangle, just upside down kind of thing. And I gave it h and x. So y is a function of time as the plane is moving. Like over here, when it was here, like the distance y here. Wow, that was not what I wanted to do. The distance y here is different than the distance y when it's at the diagonal. So it is definitely changing. And I did x because we have that the plane flies at a rate of 600 feet per second, and it's doing it horizontally, which means we should have a dx dt of 600 feet per second. Okay, so I called x of t the position of the plane as it's going that way. We have a height of 4,000. We have x is 3,000. No, those are backwards. Look at me just messing this up. I hope that didn't change my work in a second. And dy dt, this thing's changing, like the plane keeps moving this way. That's getting longer, so we want to know, the question was asking at what is it increasing at when it passes over the radio tower. So we positioned it over the radio tower. So things I have with this triangle, it doesn't ask anything about an angle, so I left out all the formulas for angles. What we have from our picture is x squared plus h squared equals y squared. And so h isn't really changing, so I plugged it in. And then we take the derivative. So we want dy dt, so we're going to take the derivative of both sides here. And the derivative of the 3,000, that's just a number, so that goes to 0. Here, it's very much like implicit differentiation, but on every single variable. The x squared becomes 2x dx dt. The y squared becomes 2y dy dt. And that should say we need y. Because we have x. We have x right here to fill in here. We have dx dt to fill in here. We want dy dt, but we need y. So let's calculate y using our original triangle. We had x squared plus h squared equals y squared. We can plug these in. I think those are backwards. So x was 4,000. No, did I have that written right there? I did have it written right there. I just had it written wrong up above. So 4,000 squared plus 3,000 squared equals y squared. You square them. The first one is 16 million. The second one is 9 million. When you add them, you get 25 million. So y squared equals 25 million. We do take the square root of both sides. And it gets plus or minus, but since we're looking at a distance, distances must be positive. So we're going to plug in, we're going to use y equals 5,000 for there. So when we plug everything in, we've got x was 4,000 feet. Dx dt was 600 feet per second. Y was 5,000. We could have technically divided by 2. I didn't. Apparently I'm a scrub. Probably should have divided by 2. I multiplied everything out. I solved for dy dt. I got 4,800,000 over 10,000. We had feet squared for the units on the left over seconds. And then feet on the right. When we clean this up, we got feet squared over feet. That's just going to leave us feet per second as our units. And when you divide these, the zeros cancel like such. And we've got 480 over 1, 480 feet per second. All right. Let's try another one. Why don't you guys try it first before we look at the example? A rocket rises vertically after launch. Alexis films the launch from 10,000 feet away. When the rocket is 2,000 feet above the launch pad, its velocity is 1,200 feet per second. If Alexis wants to keep filming the rocket, at what rate must the camera's angle change? That should say camera. So pause the video a little bit, try to figure it out, and then watch what we do. Remember, draw a picture, assign variables, figure out what values you've got, figure out which value you need, and see which equation works for that. All right. I drew my rocket here. Here's Alexis. Alexis is right there. I don't know why I gave her orange hair. She's watching a rocket take off. This is a terrible rocket. But we have X, H, and I use Y for the diagonal again. It is asking about a camera angle, and the camera angle, I didn't even draw in the camera. Oh, well, fuck it. She's got a camera. But the angle is, I did it to wherever it is, either the top of the plane, the middle of the plane, wherever it needs to be, it's still making an angle. It gave us, what information did it give us? It said 2,000 feet was 2,000 feet above. That's h equals 2,000. It says its velocity at that time is 1,200 feet per second. That is how quickly the height is changing. So we have a dH dt equals 12,000. And it said she's 10,000 feet away. So that's my other known quantity. Equations I can make here. I've got x squared plus h squared equals y squared. I can do sine of theta is opposite over hypotenuse. which is h over y. We can do cosine theta, which is adjacent over hypotenuse, which is x over y. And we do tangent theta, which is h over x, opposite over adjacent. We are looking for what rate the camera angle must change, which means we're looking for d theta dt. Okay? So with that in mind, what pieces of information do we have? We have h, we have x, and we have how quickly this is taking off. And we want how quickly this angle is changing. Stupid calls. I need to turn off my ringer. Turning it off real quick. Sorry about that, folks. There we go. So that's what we want. So which equation has all of those in it? Tangent theta had a theta, an h, and an x. Sine theta has the h and the theta, but we don't have y, and so like I avoided this one. So we're going to work off tangent theta. And so we've got tangent theta equals h over 10,000. When we take the time derivative, time, our ddt gets us secant squared theta. Then we do chain rule. The derivative of the inside is d theta dt. The derivative of h is dh dt. And we got 1 over 10,000. Secant squared theta is 1 over cosine squared theta. So like what I did is I did this, replace that with 1 over cosine squared theta. And then I multiplied both sides by cosine squared theta. And I get cosine squared theta over 10,000. DHTT we had a value for was 1,200 feet per second. So I put that in. We're looking for d theta dt. I apparently need this. I don't have theta or y. So maybe we need to figure out, like cosine theta is x over y. So we need to figure out what to do here. We did have a triangle. We had that equation we can take advantage of. Because we do have, notice that we have h and x. So we could figure out y from that, right? We could figure out y from our triangle formula and then put it into cosine theta and get cosine theta. So that's what we're going to do. So I said 10,000 squared plus 2,000 squared equaled y squared. This ends up being, when you take the square root, you get 1,000 square root of 104, which is approximately 10,198 feet. Again, we're doing distance, so we ignore the minus sign. Cosine theta, let's go back and look at our picture again. It is x over y. X was 10,000 and y was the value we just found. And I didn't turn it into a decimal because that's going to get ugly. I just plugged it in as it was. And we'll do the decimal at the end. I've got 10,000 squared over 10,198 squared. And then I've got times 1,200 over 10,000. What I ended up doing is I did 10,000 squared over 10,198 squared times 1,200 over 10,000. And this cancels one of those. So I had 10,000 times 1,200 over 10,198 squared. And I did that in the calculator. I got 0.1154 radians per second. And when I turn that to degrees, you can turn that to degrees. Radians goes to degrees by multiplying by 180 over pi. So 180 over pi times the radians gets us 6.611 degrees per second. You could have left it in radians, but like most people can't figure out or can't picture how quickly that camera's changing. So I did that. And our last section will be on cones. Let me pause this video.